of physics e-learning platform, and here is the general information about the instructor and the course. In this video we will discuss about charge distributions. So let's proceed. Well, charge distributions in general are of two types. One is scattered charge distribution, another is a continuous charge distribution. Let's try to understand the difference. In scattered charge distribution, there will be charge located at different points. Let's say Q1 is located here, Q2 will be located there, Q3 is located somewhere there. So there can be n number of charges located at different locations. So this kind of charge distribution is known as scattered charge distribution. That means they are scattered. And another type is called continuous charge distribution, in which the charges will be distributed continuously. For instance, if the charge is distributed along a line, so we will say this charge is continuous charge distribution, and we can also call it a one-dimensional charge distribution. Similarly, the charge can also be distributed on a plate or a disk, so we will say this is a continuous charge distribution on a two-dimensional body. Similarly, charge can also be distributed on a three-dimensional body, and this will be known as a continuous charge distribution. Now if we consider all the three together, then we can call it as scattered of continuous charge distribution. So that's a continuous, that's a continuous, that's a continuous separately. Well, this continuous charge distribution that we just talked about, it can be of three categories. The first one is linear charge distribution, in which the charge is distributed on one-dimensional body like wire, rod, etc. Then we will say that the charge distribution is linear charge distribution. Whenever there is a linear charge distribution, so we define charge per unit length, and that is known as linear charge density. It is denoted by lambda. Now this lambda can be written as total charge upon total length if the charge distribution is uniform, or otherwise in general we would like lambda is equal to dq upon dx. That means charge over a small x length. So this is used for variable charge distribution or any charge distribution. This can be further simplified as dq is equal to lambda dx. Now if we need to calculate the total charge, we know the total charge on that body is going to be integration dq, which will become, this is equal to integration lambda dx. So this will become the formula that we need to use in order to find out the total charge on a linear charged body where the charge distribution is uniform or non-uniform. For uniform we can use directly this. Let's take an example of a linear charge distribution. Let's say this is a uniform charge distribution case. So charge is uniformly distributed on a linear body, and charge is q, length is l. So charge per unit length, let's say linear charge density is going to be total charge divided by total length. Or if we need to write it, we can rewrite it as a total q is equal to lambda into l. So either way we can write it in case of uniform. Similarly, let's go for the next example. In this example, the charge distribution is non-uniform, is a function of x. If we need to find let's say charge on this body, so charge q on this body will be written as integration lambda dx. Now that means we are starting from here, we are measuring this as x, we are looking at this small dx length, and we are claiming on this dx length the charge reside is dq. So from here q will come out as a lambda naught will be constant, which will be coming outside, it will be x dx. If we integrate it from initial limit, which is 0, to final limit, which is L, so the total charge after integration is going to be q is equal to lambda naught, this is going to be x squared by 2, and we can put the limit from 0 to L. So total charge on this linear object is going to be lambda naught L square by 2. So in case of non-uniform, we need to use this as a formula. and we can get our answer.